Assalamu alaikum, everyone. Let's start with our class today. So we were doing complex numbers, and we are done with most of the concepts that we have in this topic. There are a few things left, and we will start with one of them today. And then hopefully by tomorrow, we should be able to complete our syllabus, inshallah. And then we could spend maybe one more session on doing some extra practice. So what have we done until now? In the last couple of classes, we talked about Argand diagrams. We talked about the modulus argument form of complex numbers. And we also discussed in the last session how to find square roots of complex numbers. That is what we have done in the last few sessions. Now, today I'm going to start with this. There is a property that we need to know about regarding products and quotients of complex numbers. Let me write that here. Product quotients of complex numbers. We want to see how their modulus and arguments are affected. Now, first of all, let me write this down here. Let's say we have a complex number like this, z equals x plus y iota. Let's say we have a complex number that looks like this. Remember, there are two other forms that we have for this as well now. One form is x plus y iota. Another way of writing the same thing is r into cos theta plus iota sine theta. And you can also write this as r e raised to power iota theta. So you should be familiar with these three forms that we have. Now, what we want to do is we want to see what happens if we were to multiply two complex numbers. Now, there's a property that we will derive from this, and it's most easily understood using this third form. So let's say I have two complex numbers like this. I have one complex number, which is z1, and that's r1 e raised to power iota theta 1. So this is one complex number that has a modulus r1 and an argument of theta 1. And I have another complex number, let's say that is z2, and it's r2 e raised to power iota theta 2. This is another complex number that I have. I have these two complex numbers. Now, I want to see what happens if I were to multiply these two numbers. Let's try doing that and see what that would give us. So if I were to multiply z1 and z2, what would that give us? r1 into e raised to power iota theta 1 multiplied by r2 into e raised to power iota theta 2. Right? That's what we get when we multiply these two complex numbers. Now let's simplify this. R1 into R2. That gives us R1, R2 into e raised to power iota theta 1 and e raised to power iota theta 2. They have the same base, that's e, so their powers are going to get added. And we get iota theta 1 plus iota theta 2. Now, if I were to take iota common from the power here, this would give us iota into theta 1 plus theta 2. So the product that we have here, z1, z2, that turns out to be r1 into r2 multiplied by e raised to power iota theta 1 plus theta 2. Now, if I were to compare this with the standard form of complex numbers that we have, this is another complex number. Now, when we multiply two complex numbers, we get another complex number from that. Remember the standard form that we have for a complex number, r e raised to power iota theta. If you compare with that standard form, you see in place of r, we have r1, r2 here. And in place of theta, we have theta 1 plus theta 2 here. So for this complex number, which is the product of z1 and z2, what we're getting is that the modulus of this complex number is r1 multiplied by r2. And the argument of this complex number is theta 1 plus theta 2. So from this result, what we can say is, what we can infer is, whenever two complex numbers are multiplied. So when two complex numbers are multiplied, their modulus are multiplied. You see, the modulus of Z1 was R1, the modulus of Z2 was R2. What about the modulus of Z1, Z2? That's turning out to be R1, R2. This is the modulus of this function, of this number, the product of those two complex numbers. And this thing is the argument. What you have in the power here with iota, this is the argument. So when two complex numbers are multiplied, what happens is their modulus are multiplied. Their moduli are multiplied. Moduli is just the plural of modulus. And their arguments, you can see what's happening to the arguments. Their arguments are added. So that is what happens when we multiply two complex numbers. This is an important result to remember. And this result basically says that the modulus of Z1, Z2 is equal to modulus of Z1 into modulus of Z2, right? And what about the argument? The argument of Z1, Z2, that means the product of two complex numbers, is equal to argument of Z1 plus the argument of Z2. Okay, so this is a rule that we need to remember. Whenever two complex numbers are multiplied, their moduli are multiplied and their arguments are added. And this is how you can represent that in mathematical form. This is one result that we have here. This is one property that we need to know about complex numbers, that when two of them are multiplied, their modulus get multiplied and their arguments get subtracted, get added, sorry. Okay. We have a similar result for division as well. So if I were to say take that same set of complex numbers, Z1 and Z2, and do the same exercise for when the two numbers are divided. So we have Z1 equals this and Z2 equals this. Now, if I were to figure out what Z1 over Z2 is, what would that be? R1 e raised to power iota theta 1 divided by R2 e raised to power iota theta 2. What result does that give us? We can take R1 and R2 outside. This whole thing is multiplied by e raised to power iota theta 1 minus iota theta 2. And we could write this as R1 over R2 into e raised to power iota theta 1 minus theta 2. And you can see here, we have another result coming out from this. If we were to compare this with the standard form of complex numbers in this in the E form, that's R e raised to power iota theta. What do we have in place of R here? In place of R, we have R1 over R2. So what's the modulus of this fraction Z1 over Z2? The modulus of this fraction is the modulus of the first complex number divided by the modulus of the second complex number. So when two complex numbers are divided, their moduli are also divided. However, what about the arguments? You can see in place of theta, we have theta 1 minus theta 2. So the arguments get subtracted. If I were to use the same language for this other result as well, this is how I could write this down. I could say when two complex numbers are divided now, so instead of multiplying, let's say they are divided. Whenever two complex numbers are divided, one divided by the other, what happens is their moduli are divided, and their arguments are subtracted. You can see that in the result here. Iota theta 1 minus theta 2, so the arguments are being subtracted and the moduli are being divided. So in mathematical form, you could write it like this: modulus of z1 over z2. So if you have a fraction like this, its modulus is just equal to the modulus of z1 divided by the modulus of z2. And if you have argument of z1 over z2, that is equal to argument of z1 minus the argument of z2. So that's what this rule means. If two complex numbers are divided, their moduli are divided and their arguments are subtracted like this. Okay, so now these are two important results to remember. You will need to use them in different contexts. You have to make sure that you remember these rules. Now, how are these going to be applied? We'll do a couple of examples now to try and understand this better. Let's start with one example. In fact, before we actually do a question, let me do this for a simple case to make sure that you understand this well. So let's say we have one complex number that looks like this: 3 minus 4 iota. This is one complex number. Let's say that's Z1. We have another complex number that is Z2, and Z2 is equal to, let's say, how can I get an integer as the modulus? Let me think about it. Okay, let's do this. So let's say we have 9 plus 12 iota. I have these two complex numbers, or let's do the other way around. Let's say we have 12 plus 9 iota. Okay, I have these two complex numbers. Now, we can find the modulus of both of these complex numbers and also the argument of both of these complex numbers. Let's try that. What's the modulus of Z1? That's square root of 3 square plus 4 square, and that gives me 5. What's the modulus of Z2? That's going to be square root of 12 squared plus 9 squared, and that should give you 15. Okay, that's the modulus of Z2. Now let's find the argument for both of them as well. We'll have to find the basic angle first of all. Basic angle, tan alpha is going to be 4 over 3. We could find the basic angle from this. Let's see what that turns out to be. Make sure your calculator is in radian mode for this. Tan inverse of 4 divided by 3. This is giving me 0.9273. It's not an exact form, but that's what I'm getting, 9273. We could do the same thing here, tan alpha for the other one, which is going to be 9 over 12. The basic angle for the other one turns out to be 0.6435. So what about the argument for the first complex number? Argument of Z1 is equal to, you can see which quadrant this is in. The real part is positive. The imaginary part is negative. So which quadrant is this going to be? It's going to be this quadrant here, right and down, the fourth quadrant. This is where this complex number is going to be. So how do you write the argument here? The basic angle is known, that's 0.9273. The argument of Z1 is going to be minus 0.9273. Remember, the complex numbers which fall in the third and fourth quadrants, we write their arguments as negative values. So 0.9273, this is what we have as the argument of Z1. What about the argument of Z2? This is the first quadrant. So the argument of Z2 is just going to be the same as the basic angle that we have, and that is equal to 0.6435. So now what we have is, we have modulus of the first complex number and also the argument of the first complex number. And at the same time, we have the modulus of the second complex number and the argument of the second complex number. So we have modulus and arguments of both of these complex numbers. Now what we can do is we can find the product of these two complex numbers. Let's find Z1 and Z2. Z1 multiplied by Z2. Let's evaluate that. Z1 into Z2. Let's see what that turns out to be. 3 minus 4 iota. That's the first complex number. And 12 plus 9 iota. This is the second complex number. If somebody was to ask me, what is the modulus of Z1 into Z2? It's going to be very simple. It would be the product of 5 and 15. So if I were to write down the modulus of this complex number, Z1, Z2, using the properties that we just did before, the modulus of the product is going to be equal to the modulus of the product of the two modulus individually. The modulus of the first one is 5. So we have 5 here multiplied by the modulus of the second one, that's 15. We multiply 5 and 15 and see what we get from that. The modulus of this product should turn out to be 75. Without even evaluating this product, we can write down its modulus. And what about the argument? We have this rule for that as well. Argument of Z1 into Z2, what is that equal to? This should be equal to argument of Z1 plus argument of Z2, right? What's the argument of Z1? Argument of Z1 is minus 0.9273. Argument of Z2, that is 0.6435. We could just add these two numbers and see what that gives us. This is giving me minus 0.2838. So that's 284. That's the argument that I'm getting for Z1 into Z2. All right. Without even evaluating this number, I can figure this out. Now I could verify this by just multiplying these two numbers and see what I get from that. 3 minus 4 iota into 12, 12 plus 9 iota, 3 into 12 is 36. 3 into 9 is 27, so that's 27 iota minus 48 iota minus 36 iota squared. And that's 72 plus 27 minus 48, that is 21 iota. Have to be. Now, if I were to find modulus, turn out to be the same. Let's try this here and see if we can verify this. Let's find the modulus of Z1 into Z2. What would that be equal to? Square root of 72 squared plus 20 squared, 21 squared. You can figure out this turns out to be 75, and that's exactly what we got here. Similarly, you could also find the argument. For that, you would first have to find the basic angle. So you'll say tan alpha equals 21 over 72. Let's see what that gives us. Tan inverse of 21 over 72. This is giving me 0.2834. 0.2838, in fact. Now, which quadrant is this? You can see the real part is positive, the imaginary part is negative. So this is going to be in the fourth quadrant as well. It's going to be right here. So how do you write the argument in this quadrant? It's going to be a negative number. So you say the argument of Z1 into Z2 is therefore equal to 0.2838, which is going to be negative, in fact, because it's the fourth quadrant. It's below the x-axis, 0.284, and that's exactly what we got here as well. All right. So if we have to find modulus of a complex number that's a product of two complex numbers, all you have to do is just multiply their individual moduli. And if you had to find the argument, you would just add the individual arguments. So this is a property that you need to know about. You can verify this for division as well, but now these are two rules that you need to remember. Whenever two complex numbers are multiplied, their moduli are multiplied and the arguments are added. That's one rule. And whenever two complex numbers are divided, their moduli are divided and their arguments are subtracted. Okay, so this is an important property that you will see being used often. Now let's do a couple of practice questions in this so we understand this well. Now let me have a look at the worksheet. Let's do a couple of questions on the worksheet on this. P3, and in this we are looking at complex numbers. Let's try some question from this. Okay, let's have a look at question number 35 from the worksheet and see if we can apply that rule here somehow. Okay, so it says the complex numbers w and z, they are defined by w equals 5 plus 3 iota and z equals 4 plus iota. We need to express iota w over z in the form x plus y iota, showing all our working and giving the exact values of x and y. Now, how is this going to work? Just have to evaluate this. Iota w over z. And the first part is simple algebra. You just input those values here. W is equal to 5 plus 3 iota. So it becomes iota into 5 plus 3 iota divided by z, which is 4 plus iota. Remember how we divide two complex numbers? We have to multiply and divide by the conjugate of the denominator. So we multiply by 4 minus iota. We also divide by 4 minus iota. That's the conjugate of the denominator. The conjugate of 4 plus iota is 4 minus iota. You multiply by that and also divide by that. Let's see what we get from this. If you simplify this, this gives us, okay, in the numerator, by the way, I have 5 iota plus 3 iota squared here, not just 3 iota. Let's simplify the numerator first. So this would become 5 iota plus 3 into minus 1, which is going to be minus 3 in the denominator. I have 4 plus iota, and I'm multiplying and dividing this by 4 minus iota. Let's simplify this and see what we get from this. If we multiply the numerators, that gives us 20 iota minus 5 iota squared minus 12 plus 3 iota, whole divided by, this is a plus b into a minus b. So that gives us 4 squared minus iota squared. All right. In the numerator, we have 20 iota plus 3 iota. That gives us 23 iota. Minus 5 into minus 1, minus 12. Whole divided by 16 minus minus 1. Let's simplify this. In the numerator, we have 5 minus 12, right? Plus 5 minus 12, that gives us 7 in the numerator. Right? Yeah, so we have minus 7 in the numerator, minus 7 plus 23 iota divided by 16 plus 1, that is 17. And now, since you want to write this in the form x plus iota y, all you have to do is just write these two things separately. Minus 7 over 17 plus 23 over 17 times iota. So this is what we get when we simplify all of that. All right. That was the first part. That was simple algebra. But now let's have a look at the second part. In the second part, it says, find WZ, and hence by considering arguments, show this thing. Now let's do this first. Let's evaluate WZ first of all, and then we'll take it from there. Part 2 of this, we know that W is equal to 5 plus 3 iota, and Z is equal to 4 plus iota. These are the two complex numbers that we're given there. We have to first evaluate their product. W times Z. What is that equal to? 5 plus 3 iota multiplied by 4 plus iota. Now 5 into 4, that gives us 20. 5 into iota, that's 5 iota plus 12 iota plus 3 iota squared, right? 20 minus 3, that's 17. And you have 17 iota from here. WZ equals this thing. So we have evaluated WZ. That's the first thing that we had to do. Now it says, by considering arguments, show this thing somehow. Now they've given us a hint. Now it's not necessary that they would always give us a hint like this, but in this case, they have given us this hint by that we have to consider arguments. Arguments of what? We have three complex numbers. We have W, we have Z, and we also have WZ now. Let's see what the arguments turn out to be. Let's find the argument of W, for instance, first of all. Argument of W, we need to evaluate this thing. That's one thing. We also need to evaluate the argument of Z, and we also need to evaluate the argument of WZ. Let's do these three things. What about the argument of W? You first have to find the basic angle. Tan alpha equals 3 over 5 and see what that gives you. Alpha equals tan inverse of 3 over 5. Now, if you notice, in the question statement, they've given us angles, but they are in their exact form. They've not used decimals there, okay? So you're not going to evaluate this argument, this value from your calculator, because you will only get a value in decimals here. We don't want decimals. You'll just leave it in this form. Okay, just leave it in this form. You don't have to evaluate this in decimals. But now you have to figure out if it's going to be positive, negative, or if you have to subtract it from somewhere. You see it's 5 plus 3 iota. Which quadrant is that? That's the first quadrant. Real part is positive, imaginary part is positive. So it's the first quadrant. So the argument of this number, W, is therefore just tan inverse of 3 over 5. This is the argument of W that we were looking for. Okay, so that's one thing that we had to evaluate. We're done with this. Let's look at argument of Z now, sorry. What about this? Z is 4 plus iota. We again first need to find the basic angle. Tan alpha equals 1 over 4. What would alpha be? Alpha would be equal to tan inverse of 1 over 4. Again, we are not going to convert this to decimals yet. Just write this in this form. Now, which quadrant is this number in? 4 plus iota. Real part is positive, imaginary part is positive. So it's the first quadrant as well. So the argument is just going to be this. Argument of Z is equal to tan inverse of 1 over 4. Okay, so we have argument of Z as well now. What about the argument of WZ? Let's figure that out. Again, we have 17 plus 17 iota here. Find the basic angle first of all. Tan alpha would be equal to 17 over 17. Alpha equals tan inverse of 17 over 17. Now, if you notice, this is actually tan inverse of 1. And tan inverse of 1 is just pi over 4. We can find an exact value for this. Tan inverse of 1 does have an exact value. We know that tan of pi over 4 is 1, right? Tan of 45 degrees, that's 1. So alpha here, therefore, is going to be pi over 4. Now, again, this is also the first quadrant, 17 plus 17 iota. The real part is positive, imaginary part is positive. So the argument of WZ, therefore, is going to be equal to pi over 4. We've got these three arguments. We've got the argument of W, and we've got the argument of Z and of WZ. Now, what exactly do we need to prove there? Let's have that in front. I'm just going to copy that thing here and try to see how we can prove this thing using what we have just calculated. Now the question asks us to do this. It asks us to prove that tan inverse of 3 over 5 plus tan inverse of 1 over 4 is equal to pi over 4. If you notice, these are exactly the three numbers that we have here. Tan inverse of 3 over 5, you've got that here. Tan inverse of 1 over 4, you have that here. And you have pi over 4, you have that on the other side. So you have to connect these three things somehow. You have a complex number W, you have a complex number Z, and you have a complex number WZ. You have their arguments. How do you connect their arguments? WZ is the product of W and Z. Using the rules that we just discussed earlier, 10 minutes ago, we can write down that argument of WZ, which is the product, argument of WZ, this should be equal to argument of W plus the argument of Z. All right? Because argument of the product of two complex numbers is equal to the sum of their individual arguments. If when two complex numbers are multiplied, their arguments are added. So argument of WZ is equal to argument of W plus argument of Z. All we have to do now is input these values here. Argument of WZ is pi over 4. Argument of W is tan inverse of 3 over 5. And argument of Z is tan inverse of 1 over 4. And that's exactly what we had to prove here. So you have to write down this statement that argument of WZ is equal to argument of W plus the argument of Z. And then you can just write down this equation. And that proves that what they've written here is correct. Okay, now you will find other questions in the worksheet and in this recent past papers where you would see something like this written: tan inverse of something plus tan inverse of something else is equal to another number. You will see that in all of those cases, you'll have to use this property that we've learned here. Okay, so for any question where you have a form like this, you will be using this particular property, that when arguments are when two complex numbers are multiplied, their arguments are added. And sometimes you'll see the division rule being used as well. When two complex numbers are divided, their arguments are subtracted. So this is how this rule is going to be used here. All right, I hope that makes sense. If you have any questions in this, let me know. Otherwise, I am going to have a look at another question. Okay, let's see what else we can do from the worksheet. This was question number 35. Okay, let's try one more question. In fact, let me see if I can find a better one. Okay, let's do this. Question number 5 from the worksheet. Let's have a look at this one. Okay, so question number 5 says, The complex number 2 plus iota is denoted by U. Its complex conjugate is denoted by U steric. We need to show on a sketch of an organ diagram with origin O, the points A, B, and C representing the complex numbers U, U star, and U plus U star respectively. And we also have to describe in geometrical terms the relationship between the 4 points O, A, B, and C. Okay, this looks like a good question, even the first part. So let's do that and see how we can represent these points on an organ diagram. We have one complex number that is U, which is 2 plus iota. We have its complex conjugate, which is U star. Let's write that down as well. What's the conjugate of 2 plus iota? It's 2 minus iota. And then you have points A, B, and C. They are represented by the complex numbers U, U star. We have them here, and also U plus U star. Okay, let's evaluate that as well. U plus U steric. U plus U conjugate, what would that be? 2 plus iota plus 2 minus iota. What does that give us? That gives us just 4. This is another point that we have. So first of all, we need to represent these points in an organ diagram, points A, B, and C. Let's do that. Let's draw an organ diagram. We have a real axis and we have an imaginary axis here. Okay, so if this is 0, this is 1, 2, 3, 4, we would have 1, 2, 3, 4 here like this, -1, -2, -3, -1, -2, and so on. Okay, so this is what an organ diagram looks like. U is 2 plus iota. Where would that be? U is going to be right here. O is the origin, right? So we had to represent 1 point O. We have represented that here. O is the origin. Then we have point A. A represents the complex number U. U is 2 plus iota. That's where this point is going to be. You will call this point A. Then B represents U conjugate, which is 2 minus iota. That is going to be right here. This is point B. Then point C represents U plus U conjugate, which is 4. Now, 4 does not have any imaginary component. It's just a real number, 4. Where is this going to be? That's going to be right here. 4, this is the point C. All right. Now, it says describe in geometrical terms the relationship between the 4 points A, O, A, B, and C. Now, how are these 4 points related? If I were to join them, what shape do you think this turns out to be? O, A, B, C. You can see all of these sides are equal. This side, this side, this side, and this side. They're all equal sides. So what shape should it be? It's a rhombus. You can say OABC, OACB, they are connected like this. You can say OACB, that is a rhombus. That's the connection between these 4 points. It's a 4-sided figure with all sides equal. That's exactly what a rhombus is. Okay, so that's the first part. This is what we had to do in the first part. Just plot those points and just say that it's a rhombus. Okay, let's look at the second part now. In the second part, it says express U over U conjugate in the form X plus iota Y, where X and Y are real. Let's do that. U over U conjugate. U was 2 plus iota. So we have to evaluate 2 plus iota divided by 2 minus iota. Now, how do we divide two complex numbers? We have to multiply and divide by the conjugate of the denominator. What's the conjugate of 2 minus iota? It's 2 plus iota. So we multiply and divide by 2 plus iota. Now in the denominator, we have a plus b into a minus b. That's going to become a square minus b square. In the numerator, we have a plus b whole squared. So we can just write it like this: a squared, which is 2 squared, plus 2 into iota, which is going to be 4 iota, plus b squared, that's iota squared. Let's simplify this. In the numerator, we get 4 plus 4 iota minus 1. And in the denominator, we have 4 minus 1. And that simplifies to 3 plus 4 iota divided by 5. You can write these two terms separately so that the real part is separate and the imaginary part is separate. And we have 3 over 5 plus 4 over 5 times iota. This is what u over u conjugate turns out to be. This is what we had to do in the second part. All right, so these are the first two parts of this question. Now let's look at the next one. In the next one, it says, by considering the argument of u over u conjugate or otherwise, prove this thing. Now again, it's that form, remember, tan inverse of something, and that's connected with something else with an equation. You would almost always have to use those rules that we discussed for when two complex numbers are multiplied and when two complex numbers are divided. We are going to be using those rules. So it says, by considering the argument of u over u conjugate. Let's start with that. Let's find the argument of u over u conjugate and see what that turns out to be. How do you find this argument? Argument of u over u conjugate. Now we have already evaluated this complex number here. For finding its argument, all we have to do is find the basic angle first of all. Tan alpha is equal to 4 over 5 divided by 3 over 5. And this gives us 4 over 3. Right? And alpha turns out to be tan inverse of 4 over 3. Now, let's look at what we have to prove here. So we have tan inverse of 4 over 3 here. So we are going to leave it in this form. We are not going to convert this to decimals. Alpha equals this. Now, which quadrant are we in? This is the first quadrant. So the argument of u over u conjugate, therefore, is just going to be tan inverse of 4 over 3. Now, where do we get this right side from? Tan inverse of 1 over 2. You see, two complex numbers are divided here. When two complex numbers are divided, so in this case, u over u conjugate, when two complex numbers are divided, their arguments are supposed to be subtracted. So what we can do is we can use this rule here that the argument of u over u conjugate, this should be equal to argument of u minus the argument of u conjugate. Okay, we can just use this. Now, do we have those two functions? Those two numbers, we know what u is. U is 2 plus iota. We can find its argument. It's the first quadrant, so the argument is going to be positive. Tan alpha equals 1 over 2. Alpha equals tan inverse of 1 over 2 for this. Now, since it's in the first quadrant, we can say the argument of u, therefore, is also just tan inverse of 1 over 2. All right. But then what about the argument of the conjugate? U conjugate is 2 minus iota, right? Let's find the basic angle. Tan alpha equals 1 over 2 here as well. And alpha equals tan inverse of 1 over 2. However, which quadrant are we in this case? The real part is positive. The imaginary part is negative. So this is going to be the fourth quadrant. It's going to be right here. Okay. Now, what about the argument then? The argument of u conjugate, therefore, is going to be minus tan inverse of 1 over 2. It's going to be a negative number because it's below the x-axis. And we write arguments in the third and fourth quadrants as negative numbers. Okay, so we have the argument of u and also the argument of u conjugate. We can just write them here. We can say the argument of u is tan inverse of 1 over 2. Subtract from that the argument of u conjugate, which is minus tan inverse of 1 over 2. On the other side, we have argument of u over u conjugate, which is tan inverse of 4 over 3. Now, if we simplify this, we get exactly that thing that we're asked to prove. Tan inverse of 4 over 3 is equal to tan inverse of 4 over 3 is equal to tan inverse of 1 over 2 minus minus, that becomes plus tan inverse of 1 over 2. So on the right side, we're going to get 2 into tan inverse of 1 over 2. And if you notice, this is exactly that we had to prove there. Tan inverse of 4 over 3, that equals 2 tan inverse of 1 over 2. And we've got that here. All right, that's what we had to prove at the end. So whenever we get something like this, an equation written in terms of tan inverse and complex numbers, usually all you have to do is apply one of these two rules that we have done. When two complex numbers are multiplied, their arguments are added, their moduli are multiplied. When two complex numbers are divided, their moduli are divided, and their arguments are subtracted. Okay, I hope that makes sense. Now today, we just wanted to do this much. In the next class, we will do the last concept that we have in complex numbers, and that's about loci. So we will see how those loci that you did in O-levels are related to complex numbers and how we're going to be using complex numbers to complex numbers in combination with loci and solve some of the problems that we have related to that. Okay, so that's what we are going to be doing next in tomorrow's class, and that's the last concept that we have left. This is it for today. I'll see you again tomorrow. Allah Hafiz.